especially about using microphone arrays for controlling directivity, controlling the location of the microphone, and so on. So I'll give the floor to Angelo for the presentation.
Thank you. Thank you to everyone for being here this morning. I will present this work, which is the result of 2 years of research, which was started from the RAI Research Center in cooperation with AIDA, which is a spin-off of the University of Parma. I see that all the other people here are working with public-funded research, a lot of European projects. In Parma, this doesn't happen. We only work with industry. And our partner give us money for doing research which is very applied to their goals. And in this case, the goal of the RAI Research Center was to create a microphone system which was capable of creating virtual microphone of variable aiming, so you can steer the microphone by software, and you can also change the directivity pattern of the microphone. And from a single probe, we managed to get currently up to 7 virtual microphones running in real time for broadcasting application. So that was the goal. As a side effect, we discovered new things. So in our case, the normal path is reversed. We don't start from theory or from basic research. We start from applied research, but we discover new things which require to come back to the theory for understanding what we did discover. Our previous experience was with the ambisonics approach with sound field microphone or the like. We did buy our first sound field microphone in '97, and then we got the DPA4 microphone, the tetramic, and this is our own ambisonic solution. It's called the Brahma, and one sample of this Brahma is in the listening in the demo room outside. This is the very old origin of ambisonics. Due to Michael Gerdon and Peter Craven in the 70s. And here you see the very first prototype of the sound field microphone, and this is our current one. The ambisonic theory is based on analysis of the sound field, which require only 4 channels for describing it completely, which are pressure and the 3 Cartesian components of particle velocity. And the sound field microphone delivers these signals by an analog processing box, which is this small black box here. This is how an actual sound field microphone behaves, not really very well. You see the polar patterns are not always perfectly aligned with the Cartesian reference, and the amplitude of the velocity component becomes very big, too much large at high frequency. So it's not working very well. But we managed to solve this problem, creating a digital approach for creating the signal from the capsule, which is already a very first application of virtual microphones. In practice, we did build what is called an A-format microphone system, modifying a very cheap and economical Zoom recorder, mounting a probe on it, and this probe, of course, is a tetrahedron like the original sound field microphone. These are 4 cartridge microphones. We record directly the signal from the capsule. This is the so-called A-format signal. It says to be converted in B format. Mostly we use this system for measuring impulse response in rooms with pulsive source. That is a very cheap and clever solution for measuring impulse response in a room. Here we are in a Greek theater outdoors. Okay. The signals have to be converted to B format. We do this virtual microphone rendering by means of a matrix of 16 FIR filters. And for implementing these filters in real time, we developed a free VST plugin, which is called Xvolver, and which you can download from our website. So if you go on my website, you will be able to download this VST plugin, which can have any number of inputs, any number of outputs, up to 32 inputs, 32 outputs. You load a matrix of FIR filter, and it does the convolution. In this case, the plugin is working with 4 inputs, which enter in the matrix from above, and the result of the convolution comes horizontally out on the right. So every output is the sum of the 4 convolution of the 4 capsule signal multiplied by the proper FIR filters. After you get the deformat impulse response of your room, you can analyze it in the traditional way, computing reverberation time and the other acoustical parameter, even spatial parameter, of course. But what is very interesting is the spatial analysis of the room. And we want to localize the direction of variable of the sound. I don't know why it is so small now. What's happening here? For some reason, the font is too small. Now it's probably too. Okay. See what happened. Okay, we compute the sound intensity. The vector of the sound intensity give you the. Something went broken. Okay, the theory, you will find the theory for doing this analysis on the presentation on my website. In any case, just the sound intensity vector is employed for doing the computation. What we want to do is to show where the sound is coming from over an image of the room, a panoramic image. And for creating this image, we use the Mercator projection, like with the world mapped on a flat plane. There is a very nice free software from Microsoft called Image Composite Editor. You make a lot of pictures with your small compact camera around the microphone position, and this software stitches the picture together, creating the image of the whole room. And after you do that, we can plot the reflection over the image with a circle. The circle is made proportional to the sound intensity level, the size of the circle. The transparency of the circle is made proportional to the reactivity ratio R, so if the sound field is very active, the circle is very opaque, and instead if the circle appears transparent, it means that the reactivity was high, there was no active field in that time. So let me try to see what happens. Here we are in a concert hall in Patras in Greece, and we measure the impulse response. You see the impulse response here below. There are two curves. In blue, you see the sound intensity, and in gray, you see the energy density. When the sound intensity is close to the energy density, the sound field is very active. When the sound intensity is low compared to the energy density, it means that the sound field is very reactive. The sound is diffuse, and there is not a lot of energy traveling in a precise direction. Let me see the animation of what happens during the playback. The direct sound was in the center, of course. Now there are smaller reflections, but the circle is almost transparent. Instead, when you get some strong reflection, like here, there is an echo, you will be able to see where the echo is coming from above, actually, you see. The circle went up, because there is the ceiling causing this kind of reflection which you see here. And this is very active, because the blue line is very close to the gray one. Another example outdoors, again in Greece, this is an open-air theater, of course, and you see the reflection coming from the gradons all around, and not anymore from the sheen. Okay? Now we not use only the spherical, the tetrahedral array with just 4 capsules. We have got a couple of eigenmites. The third one was ordered past week, and the fourth one, the one we will stay in property of the University of Parma, will be ordered next week. So the first two are property of Rai, of course. The eigenmite is an high-order ambisonic third-order deformat array, but we developed as different technology for deriving virtual microphones from it, which is direct numerical synthesis, a matrix of FIR filters, exactly as we did with the tetrahedral probe for making the deformat signal. And now we have a very new approach, which is called spatial PCM sampling, and I will try to explain it very quickly to you today. The time is short. This was our first spherical array 2 years ago. It's now in Spain, in Valencia. It has to come back next week. This is the Eigenmic. It's equipped with a network interface allowing a very long cable. This is very important for broadcasting application for live. The creation of virtual microphones made by Eigenmic is employing high-order ambisonics, high-order spherical harmonics, and this is a problem because the high-order spherical harmonics are signals which tend to be very noisy and very band limited. This means that the resulting virtual microphone array don't have a pattern which is constant with frequency. They can be narrow in a central frequency range, but they give up directivity at very low frequency or very high frequency. So we have this kind of problem with the high-order ambisonics technology, and we developed an alternative technology which is not anymore ambisonics based for creating much narrower microphone array with sharper directivity pattern, lower noise and wider frequency range. The idea was to make a direct synthesis of the virtual microphone, again employing X-border, so employing a sum of convolution. As you see, the equation is very simple. You get your signal from the microphones, you apply a number of FIR filters, and you sum the result. Very simple. The trick is how to design the filter coefficient. We don't use any theory. Our solution is completely numerical. We measure the impulse response of our microphone. We get a matrix of measured impulse response. We invert that matrix, and that's all. I am not going to explain all the details here. You find it in my papers. So we go very quickly on the slides which describe the measurements of the impulse response of our microphone array. This is our target directivity. Our virtual microphone is designed to be a cardioid of a high-order cardioid. We impose that the filter applied to the measured impulse response produce the prescribed directivity function of your target microphone. We get a system, which is the one below here, where the filters applied to the measured data should be identical to the prescribed directivity pattern plus some modelization delay. At the end of the long history, we get this equation which gives you the matrix of filters. We apply a regularization parameter. We make the inversion very accurate in a central frequency range and less accurate at extreme frequencies, very low and very high. This summarizes the whole process. And we can create directed cardioids, ultra-directed cardioids up to 6 orders. Measurements done inside the anechoic room for capturing the spatial information of our microphone with the sine-width method, of course. This is the support for rotating the microphone inside the room. And then we also made a reference measurement with a turntable just for controlling how the pattern comes out. After we designed our matrix, inverse matrix of filter, we designed a real-time microphone system. First of all, there is a parabolic mirror camera, which creates the background image live for seeing where you point your microphones, following the actor on the stage, for example. With the mouse or the joystick, you can control where the beams are pointing. And then we have a software which runs on a portable Macintosh computer, which makes up to 7 virtual microphones in real time. This is the system, and you will see it mounted in the demo room outside, and we'll be able to play, make some short recording, and then listen to the sound. There will be a lot of confusion in that room, which is very good for our application, because we can create a very direct virtual microphone, picking up the sound of someone talking in the middle of a lot of confusion. This is the video unwrapping part. This was written by my son. Is a very small processing program. Processing is a programming language, and it takes the image coming from the mirror, this parabolic mirror, and unwraps the image, creating a panoramic video, like the Microsoft software with photos. But this is done in real time with video. This is an example of what happens when you move your virtual microphone around during a recording. Well, this is during playback actually, but it is the same. That's me. That's Andrea.
I'm trying to some words.
My son is here behind playing some music with a phone. That's the music. Now the virtual microphone is pointing on the cellular phone. I am also talking, but my voice is low. Now you hear Andrea. And now you hear me. Okay, I think is enough. RAI employed this system for recording concert, operas. This was La Bohème in Turin. They made a very nice 7.1 recording with surround. So some virtual microphones capture the room reverb, some other capture the direct sound from the stage. We have a very short example, but here is just in stereo, so you don't hear the surround here. What's important is the sound quality. Other microphone system, array microphone system, have a bad sound quality. This is really broadcasting quality. The capsules of the mic are made by Sennheiser. They are top-grade microphones. And our processing managed to keep the quality over the whole processing chain. So these signals are ready for production, and already 2 operas were broadcasted live from Turin with the mic and our processing software. Not a glitch, not a noise, nothing. It works very reliably. And now let's see the new theory, the spatial PCM sampling. We understood that we can create not just 7, but 32 virtual microphones. 32 very directed virtual microphones pointing in the same direction of the capsule. And this goes exactly in that idea of creating a connection between time sampling and spatial sampling, and creating something which is in space the equivalent of PCM in time for a waveform. This picture shows this comparison. On the left, you have a traditional waveform in time, and when you make PCM sampling, what you do is to model this waveform as a sequence in time of pulses of given amplitudes. And what you are coding is actually the amplitude of these pulses. We are doing the same in space. We model a generic complex directivity pattern as a number of spatial direct pulses pointing in many directions around, in many, currently in 32. This model is very powerful. Going ahead in the comparison, you can see how the Fourier expansion of a waveform is exactly what ambisonics does in space. The ambisonics representation of the spatial sampling is with spherical harmonics, which means spatial frequency. So as ambisonics is the waveform the spatial representation by means of a number of, say, spatial sinusoids, the same is in time. A generic waveform can be expressed as the sum of a number of sinusoids with proper amplitudes. It's the same. This means that we are sampling the space with a number of very directed virtual microphones pointing in the same direction of the capsule and more or less uniformly covering the whole spherical horizon. This is the overplot of the axis of those virtual microphones over a panoramic image of the Colosseum in Rome. How can we process the results of these 32 virtual microphone, this signal? First of all, we generate the output by using Xvolver again. In this case, we have 32 inputs, 32 outputs. Its solver is so efficient that it can do this processing in real time with a modern computer, of course, and with filters which can belong up to 2 kilopoints or even 4 kilopoints. No problem with that. Now, we did employ first this approach, again, for measuring impulse response and for analyzing the spatial property of the sampling rooms. We measured only 2 rooms till now. Our Sala dei Concerti in Parma and the Teatro La Scala here in Milan. Here are where the measurements were done, and here you see the system mounted on the stage of La Scala. Here you see the panoramic image of the 2 rooms, and here you see the animation, the video showing you the analysis, the spatial analysis of the impulse response in La Scala. That's the direct sound. You see, it was on the left because the loudspeaker was on the left of the microphone. Now there is a reflection, is arriving. There you see the reflection, which comes from behind the loudspeaker currently. It comes from the wall behind the loudspeaker. So this kind of spatial analysis show you from where the sound is coming. We have now the same for our Sala dei Concerti in Parma. In this case, the direct sound is exactly in front of the microphone, but there are room reflections from above, from the side wall you have seen, and now there is one from the back wall, which is quite annoying because in this room it is a sort of echo. You have seen that. Very loud coming from behind. Okay. The spatial PCM sampling can be also a very good way for rendering the recording because, again, with a matrix of FIR filters, we can feed directly the loudspeaker in a loudspeaker array, recreating the sound field inside the listening room, inside the playback system, which replicates the original recording made with the Eigenmic in the original room. In practice, we use the same theory which we employ for creating the encoding filters. We use it also for creating the decoding filter. We place the Eigenmic at the center of the loudspeaker array. We measure all the impulse response key, key 1, key 2, key 16, from every loudspeaker to the Eigenmic. And again, we impose that we get what we want. That is the concept of this numerical solution with no theory. We want something, and we say, okay, Mr. MATLAB, give us the solution. And he's very clever, and gives us a very nice solution, with no theory at all. We don't know anything about wave equation, ring function. Oh, it's cut completely, no problem. It takes count of everything. All the reflection of the room is working with the room, inside the room. So the filters know of the room, and the inverter create the inverse filter which reverberate the room and provides you perfect listening where the microphone was placed. The only problem of this approach is that it is a sweet spot solution. If you go with your head where the microphone was, the sound is perfect. If you move 1 or 2 meters far, it doesn't work anymore so well. We have tested this system in 2 environments. One was tested by our colleague and friend Filippo Pazzi at ISQR, where they built this very nice spherical loudspeaker system, and then there is no room to be corrected. So it was in an echoic room, it worked perfectly. We are very recently managed to have it working in our listening room, which you see on the right, which is equipped with only 16 loudspeakers and is not absolutely anechoic, but it still works, proving that it is possible to manage also the environment. This is how our listening room is configured with the different loudspeaker array. We are using the 16 blue loudspeaker for the, this kind of application. In Parma, we also have a wave synthesis playback room, but it is only 2-dimensional. In this case, we have 176 loudspeakers embedded in the walls. This room is capable of 30 seats and is used inside the facility of Casa del Suono, which is a museum in Parma. Conclusion. Our new FIR-based virtual micro technology creates very good super directed microphones, very nice for broadcasting applications. And we can move them in real time following the actor on the screen or something like that. We can make a complex spatial analysis of the sound field employing this novel SPS approach with 32 ultra-directed virtual microphone, and this allows for spatial analysis of the room reflection inside a concert hall. It also allows for very easy spatial sound reproduction in a three-dimensional loudspeaker array. Thank you.